Fatigue. Fatigue design. In the design of tubular connections, due considerations are being given to the fatigue action as related to local cyclic stresses. Detailed fatigue analysis will be performed for all structures. It is recommended that a spectral analysis technique be used. Other rational methods may be used provided adequate representation of the forces and member response can be demonstrated. Caissons, monopods, and similar non-structures deserve detailed analysis with consideration where vortex setting were applicable. Fatigue analysis in general. A detailed analysis of cumulative fatigue damage when required shall be performed as described in the following steps. Wave climate. Wave climate should be derived as the aggregate of all sea states to be expected over the long term. And this may be condensed for purpose of structural analysis into representative sea states characterized by wave energy and physical parameters together with the probability of occurrence. Space frame analysis. Space frame analysis will be performed to obtain the structural response in terms of nominal member stress for a given wave force applied to the structure. In general, wave force calculation should follow the procedures. However, current may be neglected, and therefore consideration for apparent wave period and current block gauge are not necessary. Here, one thing we should understand that wave forces should follow the procedures. Current may be neglected. In the space frame analysis, we could neglect the current. So if we neglecting the current, apparent wave period and current blockage factor, these two becomes these are not necessary. So space frame analysis, we are doing it to obtain the structural response in terms of nominal member stress for a given forces. So structural response means nominal member stresses we are getting for the given wave forces that are applied to the structure. Once you apply the wave forces on the structure will respond in terms of its nominal member stress. So those values we need to obtain nominal member stress to calculate the fatigue analysis. And to do that, wave climate should be derived as aggregate of all sea states. So it's not a one single state, it's an aggregate of all sea states to be expected over long term. So in the long term, what are the sea states we are expecting? That aggregate is the wave climate. That we need to use it. This may be condensed for purpose of structural analysis into representative sea states characterized by wave energy spectra. So wave climate we are representing by using wave energy spectra and physical parameters together with probability of occurrence. So we need spectra, wave energy spectra, physical parameters also with their probability of occurrence. With these we can define or derive the wave climate. Detailed analysis of cumulative fatigue damage. Fatigue means it's not a single thing, it's a cumulative. When required shall be performed as the following steps. So to calculate the fatigue, detailed analysis of cumulative fatigue damage, we need to do it. Okay, fatigue design of tubular connections. Wherever we have the tubular connections, we need to give due consideration for the fatigue action as related to local cyclic stresses. We need to give fatigue action that is a local cyclic stresses we need to consider. Detailed fatigue analysis will be performed for all structures. It's not a simplified fatigue analysis. Detailed fatigue analysis we need to do it. It is recommended that a spectral analysis to be used. So usually spectral analysis is the recommended method of analysis. Other rational methods may be used provided adequate representation of forces member response can be demonstrated. So if we are possible to demonstrate the adequate representation of forces and member response will be displacement, these things, but mainly we are interested in getting the stresses. As you see here, mainly we are interested in getting the structure response in terms of nominal member stress for a given wave force applied to the structure. Okay, caisson, monopod, and similar non-jacket structures deserve detailed analysis. So these kind of caisson, monopod, non-jacket structures, these do not have any most of the redundant members. So these deserve detailed analysis with consideration of what actioning were applicable. There's one simple monopod structure, and here you can see the stress versus number of cycles. You see endurance limit. Endurance limit says that at a particular stress, if you apply number of cycles infinity, it doesn't cause any failure. So this is a particular stress level, very low stress level, that can be applied n number of cycles. That means infinity number of cycles. Even if you apply that many number of cycles, it can withstand. That's called endurance limit. So stress versus number of cycles, that is something called endurance limit. Okay, that's the endurance limit. Stress will not, at this particular stress, you can apply n number of cycles. Kinematics factor equal to 1 and conductor shielding factor equal to 1 should be applied for the fatigue waves. The drag and inertia coefficients depends on the C state level as parameterized by the Kelvin-Carpenter number. For small waves, that means Kelvin-Carpenter number less than 1 and greater than 1 less than 6 for platform legs at mean water level. For small waves, value of cm2 and cd 0.8 for rough members and cd equal to 0.5 for smooth members would be used. So CD is 0.8 high for rough members and low for smooth members 0.5. CM is same only. Guidelines for considering directionality, spreading, dyes and marine growth are provided in the commentary for this. Spectral fatigue analysis. Spectral analysis techniques should be used to determine the stress response for each C state. Dynamic efforts should be considered for C states having significant energy near platform's natural period. Local stresses. Local stresses that occur within the tubular connections should be considered in terms of hotspot stresses located immediately adjacent to the intersection using suitable ACFs. The microscale effects occurring at the toe of the weld are reflected in the appropriate choice of ascent curve. Here we could see one more thing also. Spectral analysis techniques should be used to determine the stress response for each C state. So for each C state we need to get the stress response. Dynamic effects should be considered for C states having significant energy near platform's natural period. So if the C state has sufficient energy near the platform natural period, if the platform natural period has say around 1.2 seconds, 3 seconds, 2 seconds, something like that. If the C state is also having the sufficient energy, then dynamic effect should be considered. Fatigues are small waves. So for small waves, CM value of 2 and CD value of 0.8 for rough and CD of 0.5 for smooth should be considered. So smooth is having less CD value, drag value, but for rough member, CD value is 0.8. Drag and inertia coefficient depend on the C state level. So it depends on the C state level, only the drag and inertia coefficients are there. These are parameterized by Kelvin-Carpenter number K. So, and moreover, directionality, spreading, tides, marine growth. This also should consider. Guidelines are available. Important thing is that kinematics factor 1 and conductor shielding factor are also equal to 1 should be applied for the fatigue waves. So kinematics factor and shielding factor, both it's 1.0. Local stresses that occur within the tubular connection should be considered in terms of, so we need to consider the local stresses within the tubular connection in terms of hotspot stresses located immediately adjacent to the joint intersection using suitable ACFs. So we need to use the suitable STFs. Microscale effects occurring at the toe of the weld are reflected in the appropriate choice of. So microscale effects occurring at the toe of the weld. So that is also reflected That means that is also considered micro scale effect. Stress responses for each location around each member intersection of interest in the structure. The stress response for each C state should be computed, giving adequate consideration to both global and local stress effects. The stress response shall be combined into long-term stress distribution, which should then be used to calculate the cumulative fatigue damage. N is the number of cycles applied to the given stress range. Capital N is the number of cycles for which the given stress range would be allowed by the appropriation curve. Alternatively, the damage ratio may be computed for each C state and combined to obtain the cumulative damage ratio. And fatigue life safety factors in general. The design fatigue life of each joint and member shall not be less than the intended service life of the structure multiplied by the safety factor. For the design fatigue life, the cumulative fatigue damage D should not exceed unity. For institute conditions, safety factor for fatigue steel components shall depend on the failure consequence. That depends on the criticality and in-service inspectability. Critical elements are those whose sole failure could be catastrophic. In lieu of a more detailed safety assessment of category L1 structures, the safety factor 2 is recommended for inspectable and non-failure critical connections. For failure critical and or non-inspectable connections, increased safety factors are recommended. Reduced safety factors is recommended for category L2, L3 conventional steel structures on the basis of in-service performance data. Safety factor 1 for redundant diver or ROV inspectable framing, with safety factors for other cases being half those in table. So here one thing we need to understand that stress response for each location around each member intersection of the interest in structure, the stress response for each C state should be computed. So we have here each location, each member, each location, and each C state. So we need to give the due consideration, giving adequate consideration to both global and local stress effects. So we need to consider both global as well as local stress effects also. The stress response shall be computed into the long-term stress distribution, which should then be used to calculate the cumulative fatigue damage ratio. Cumulative fatigue means actual number of cycles, that is the number of cycles applied at a given stress range. This is the stress range. Stress range means what's the maximum positive and negative, or what's the maximum and minimum. That's the stress range. N is the number of cycles for which given stress range would be allowed. So this is the stress range, means this stress range can be going only this many number of cycles, like allowable number of cycles. That is allowed by appropriation curve. So in SN curve it will define the allowable number of cycles. So this ratio, it gives you the damage ratio. Damage ratio will be for each C state combined to obtain the cumulative damage ratio. So damage ratio for each C state needs to be computed, and then we can combine it to obtain the cumulative damage ratio. Fatigue life safety factors. So this concept, the concept behind this life safety factor is that in general, the design fatigue life of each joint member shall not be less than the intended service life. For example, maybe structure as intended service life of 30 years. It should be multiplied by a safety factor, and then the design fatigue life should not be less than that intended service life multiplied by safety factor. For a design fatigue life, cumulative fatigue damage ratio shall not exceed unity. So for the design fatigue life, this damage ratio shall not exceed the unity. In steel conditions, safety factor for fatigue of steel components shall depend on the failure consequence. So there are two things. One is criticality, and another one is inspectability. If it is inspectable and critical, that will have different factor of safety, and if it is non-critical and inspectable, or inspectable, non-critical, critical, and non-inspectable, there are different combinations. So instead of so critical elements are those whose sole failure could be catastrophic. So whole sole failure could be catastrophic. That's the critical elements. In lieu of more detailed safety assessment of Category 1, Safety Factor 2 is recommended for inspectable non-failure and failure critical or non-inspectable connections. Increased safety factors are recommended. You will see in this table what are the increased safety factors. Reduced safety factors recommended for L2, L3 for conventional steel structures on the basis of in-service performance. If you have the in-service performance or proper non-conventional steel structures for Category L2 and L3, reduced factor safety can be used. Fatigue life safety factor. So whether it's a failure critical or non-critical, inspectable or non-inspectable, based on this we can see the fatigue life safety factors. If it is critical or non-inspectable, it goes as much as 10 factor, it goes as much as 10 if it is critical and non-inspectable. If it is non-critical and inspectable, it goes to 2. So 2, 5, 10. These are the fatigue life safety factors depending upon the criticality and inspectability. When fatigue damage can occur due to other cyclic loadings such as transportation, the following shall be satisfied. That means it needs to be accumulator. DJ is the fatigue damage ratio of each type of loading and is a factor of safety, associated safety factor. For transportation, where long-term wave distributions are used to predict short-term damage, a larger safety factor should be considered. It means like as transportation, where long-term wave distribution are used to predict short-term damage, and means that larger safety factors should be considered.